So we're working with section 3.6, curve sketching. This is part 2 of my videos for this section. I'm going to be doing the next 2 examples on the slideshow. So again, with these, try to do it on your own. Pause the video, then come back and I'll work through it with you here. So we're down to this one here next. X over the square root of x squared plus 2. So give this one a try. So again, we're going to start off looking at domain and range. If we look at this one, my denominator is square root of x squared plus 2. X squared plus 2 is always positive. I can put in any real number. So there are no vertical asymptotes. My domain is going to be all real numbers. If I look for, so I want to look at what's the end behavior, what's the horizontal asymptotes going to look like. So let's look at the limit as x approaches infinity of x over the square root of x squared plus 2. So we're going to take this and divide top and bottom by x. On the top, I'll divide by x. On the bottom, I'm going to divide by the square root of x squared, so I can take it into my square root. I'm going to get my limit as x approaches infinity of 1 over the square root of 1 plus 2 over x squared. Which comes down to 1. But now I got to take a look and see, go back to the original problem. What happens at positive infinity? As we're going to positive infinity, this is going to be positive, this will always be positive, so we go to 1. If I'm looking at the limit as x approaches negative infinity, the numerator is going to be negative, denominator is still going to be positive, so in this case, I'm going to get negative 1. So for horizontal asymptotes, I'm going to have x equals plus or minus 1. And actually, let's rewrite this. As x approaches positive infinity, I'm going to have f of x approaches 1. As x approaches negative infinity, I'm going to have f of x approaches negative 1. So I got to keep track of those. Again, it's not always when we have a horizontal asymptote, it doesn't always have the same asymptote for both sides. So, next let's look for zeros. My x-intercepts, I'm going to get that where if x equals 0. So that's going to be the point 0, 0. So this is also going to be my y-intercept. Is going to be the point 0, 0. I'm not going to have any other x-intercepts on this one. Now let's come down to our first derivative. So, again, I got my lovely quotient rule here. F prime of x is going to be x squared plus 2 to the 1/2 times the derivative of x minus x times the derivative of that, so that's going to be 1/2 times x squared plus 2 to the negative 1/2 times the derivative of x squared plus 2 is 2x. Don't forget your chain rule. Over x squared plus 2. And to square the square root, I just get x squared plus 2. Oh, that's kind of nice. Let's play with this a little bit. I got x squared plus... No, I'm going to write this with square roots. Square root of x squared plus 2 minus... I got 4x squared over 2 times the square root of x squared plus 2. And I'm going to make a common denominator here. So I'll go square root of x squared plus 2 over square root of x squared plus 2. And these two will give me... I'll take this down to the denominator. So in the bottom here, now I got x squared plus 2 to the 3 halves. Because here I have a square root times, I got one basically, yeah. That squared is going to be x squared plus 2 minus 4x squared. Oh, I messed up here. Sorry about that. 2 times 1/2 cancels out. So let's fix that. So this isn't a 4x squared. This isn't a 4x squared, which makes everything so much nicer because those cancel out. And my first derivative is just going to be 2 over x squared plus 2 to the 3 halves. And you notice that's not going to have any critical points because this will never equal 0. And it denominator never equals 0. So this is no critical points. There will be no relative maxima, relative extrema, period, on this problem. This graph, let's see. 3 halves. So no critical points. So now let's look at second derivative. Second derivative. Well, before I work on the second derivative here, I'm going to rewrite the first derivative to be 2 times x squared plus 2 to the negative 3 halves. So I don't have to use the quotient rule or anything like that. That's just 2 times a negative 3 halves times x squared plus 2 to the negative 5 halves times the derivative of x squared plus 2. So we get, oh, the 2 and the 3 halves, the 2 there cancel. So I'm going to end up with a negative 6x over x squared plus 2 to the 5 halves. And if I look for possible inflection points, where does this equal 0? At x equals 0. So we have a possible inflection point at 0, 0. So, yeah. I'm going to make this 1, 2, because my asymptotes, I have end behavior asymptotes at 1 and -1. My only inflection point is going to be right here. So I don't have any relative extremas, so I'm not going to come above and go back down. So I may as well stretch this out on the y. I have a point I know at 0, 0. And I have my horizontal asymptote. When I'm positive, my asymptote is up here at +1. When I'm negative, my asymptote is down here at -1. All I have, my intervals are going to be -infinity to 0 and 0 to infinity, because that's my only possible inflection point is right here as well. So I'll plug in, well, let's see, if we put in second derivative at -5, numerator is going to be positive, denominator is always positive, so this is greater than 0. This is concave up. So it's going to be kind of looking like this, coming down to that asymptote. That's a pretty bad sketch there. If I look at someplace over here, I'll look at +5. That's going to make my numerator negative. My denominator is always positive. This will be less than 0, so that's concave down. So that's going to look like that. Woohoo! One more sketch done. Let's look at the next one. So again, if you haven't tried this already, whoops, let's actually bring it up. If you haven't tried this one already, give it a try right now. Because this is a polynomial. Well, not quite a polynomial, but it's kind of like a polynomial. Right? Let's scratch that off. 2x to a power minus 5x to a power. They're positive exponents, so this is going to have a domain of all real numbers. So I don't have to worry about any vertical asymptotes on here. If I look at horizontal asymptotes, what's going to happen as x gets huge? As x gets big in the positive direction, we can kind of look at this and say, here we're going to an odd power, fifth power. So this is 5/3 is bigger than 4/3. This is going to overpower at big values. It's going to be an odd power, so it's going to keep the sign. So my end behavior is going to be as x approaches infinity, f of x is going to approach infinity. And as x approaches negative infinity, f of x approaches negative infinity. Because you plug in infinity here, you get infinity minus infinity. Yeah, that's kind of weird. But again, this is the bigger power, so eventually this is going to be left behind. Even though 5/3, 4/3 are pretty close, infinity is infinity, right? So we kind of know we got this type of behavior looking at that. So let's go start looking at zeros. If we want 2x to the 5/3 minus 5x to the 4/3 to equal 0, I have a common factor of x to the 4/3, and that's going to be 2x minus 5. I should probably be writing over here, but so I'm going to have x equals 0 and x equals 5 halves, or 2.5, are going to be my two zeros on here. No, I messed that up. Totally. I'm not going to redo this whole thing. This is x to the 1/3. Sheesh. How can you do that to us, right? Okay, so we do have x equals 0 was 1 from here, but we need 2x to the 1/3 equals 5. So x to the 1/3 equals 5 halves. So x equals 5 halves cubed, which is 15.625. Unless you want to say 125 over 8. If you like the fractions, go with it. Since we're graphing, I'm going to go with the decimal here. So let me write these down so I can remember them. So we have x-intercepts are going to be at 0, 0, and at 0, 15.625. So obviously I'm going to have a y-intercept then at 0 as well. Now let's go with our derivatives. At least the derivatives are easy on this one, right? 2 times 5/3 times x to the 2/3 minus 5 times 4/3 times x to the 1/3. Again, why am I doing this way? I'm forgetting what I'm doing already. Makes it so much easier if I do it this way. Okay. So this is going to be 10/3 times x to the 2/3 minus 20/3 x to the 1/3. Or I can say that's 10/3 times x to the 2/3 minus minus 2x to the 1/3. Okay, I want to look for possible critical points. So my critical points, I'm going to set this equal to 0. So I really have x to the 2/3 minus 2x to the 1/3 has to equal 0. Or x to the 1/3 times x to the 1/3 minus 2 has to equal 0. So I get x equals 0, or x to the 1/3 equals 2, so x equals 8. So I look at that point, again, 0 is going to give me the point 0, 0. I plug in 8. 8 plugged into this equation is going to give me 16. So I'm going to have critical points at 0, 0 and at 8, 16. Let's go to our second derivative. Second derivative is going to be 10/3 times the derivative of x to the 2/3. 2/3 x to the negative 1/3 minus 2 times 1/3 times x to the negative 2/3. So let's try to neaten this up again. Here's 2/3. Here's 2/3. So we're going to have 20 over 9 on the outside. I got 1 over x to the 1/3 minus 1 over x to the 2/3. I'll make that a common denominator. So I'll go x to the 1/3, x to the 1/3. So I'll get 20 over 9 times x to the 1/3 minus 1 over x to the 2/3. So we got to look and see where do we have possible critical points. Sorry, not critical points, inflection points. Well, if x is 0, this does not exist. So 0, 0 is a possible inflection point. So we also have where x to the 1/3 minus 1 equals 0. So this is going to be x equals 1. So we plug 1 into this function. 1, 1, we got 2 minus 5, that's a negative 3. So these are my possible inflection points. Are 0, 0, 1, negative 3. So when I'm looking at setting up my intervals, my test intervals, I'm going to look negative infinity to 0, 0 to 1, 1 to negative 3. And I'm going to remember these two are my critical points. So let's look at concavity first for here. So if we pick a point on here, f double prime, let's go at negative 5. If we look at the second derivative, this is always positive. This is always positive because it's an even power. So here a negative number will make this a negative minus. So this is going to be a negative. So this is going to be less than 0. This is concave down. At between 0 and 1, if we plug in 1/2, again we're positive here, positive, but 1/2 to the 1/3 power is going to be less than 1, so this is still negative. So this is also, you notice both of these are concave down. Concavity doesn't change, so that's not an inflection point, which makes sense because it's a critical point. If we plug in 0, f double prime of 0 is going to be, again, a negative. Well, f prime of 0 does not exist, right? Because I can't do this. So this, we can't use the second derivative test to check that critical point. So let's try the first derivative test. F prime at negative 5. So we look at here. That's going to be, so negative 5 squared, so that's going to be positive, minus a negative. This is going to be greater than 0, so this is increasing. If we go f double prime at 1/2, we take 1/2 squared is going to be, in the cube root of 1/2 squared is going to be less than 2. So when we take -2, yeah, it's going to be negative here. So here we're less than 0. So this is a relative max, which makes sense. It's concave down, so this should be a relative max. And we're concave down for this entire interval. We look at 1, -3, so let's try 1, -3. Why am I going to -3? I don't know. It's been a long morning, obviously. This is 1 to infinity. So we will check that at, let's go with just at 5. So again, 5 to the 1/3 power is going to be bigger than 1. So that's positive, positive, positive. This is greater than 0, so we're concave up. So we put all of this together. Let's go with, this is up, this is down, this is down. Oh, we should have checked at 8. At 8, the same thing's going to fly, though. 8 to the 1/3 is going to be 2. 2 minus 1 is 1. So this is positive. So this is concave up again. This is a relative minimum. So let's draw this graph. So here I got to get out at least to 8. Oh, I have to get out to at least here. 15.625 is my 0. So I want to get out to, let's maybe make this go a little farther here. Let's move this out. Let's just cancel and do it this way. Let's draw a new one. Okay. So we'll go with 10, 20, -5 here. I'm going to go -10, -20, because I need to get down to -16. I got that wrong. -16 on the y there. I know I'm at the point here, 0, 0. I know I'm at the point 15.625, 0. I know at 0, 0 I'm a relative max. At 8, -16. I'm at a relative min. I know at 1, -3. I have an inflection point. So here I'm concave down, so I'm going to go like this, and then go down forever. Here I'm going to switch to concave up, go to that point, come back up through, and go like that. So that's my sketch of my graph for this one. Oh boy, half an hour. We did 2 problems. Lovely stuff. So again, I'll do the other 2 problems on another video. Here are your problems you should be working on.